Let's do these. Okay, so pause and read the question. Okay, so the first thing we got to do is figure out whether this is a mean problem or a proportion problem. Mean problems, they're going to say the words mean or average. They're going to give you a standard deviation. Proportion problems, we're always talking about what percentage of somebody did something. This is a proportion problem. Think proportion means percentage. Those mean kind of the same thing. So this is a proportion problem. So let's start by figuring out what's our population, 65% of who? Of people. So I'm just writing this down to help me write the next line. So our population is people. Worldwide. What are we calling success? What did they do? What did the people do? They used Google Chrome. So now we can define our variable. It's not necessary to write those two down. I'm just writing them down for your benefit. This one is required. Then when I say define your variable, this is what I mean. Let P, which is the population proportion of success, be the proportion of these that did that, the proportion of the population that was successful. So let P be the proportion of people that use Chrome. That's defining our variable in these proportion problems. We're told that P equals 0.654. I want to turn that into a decimal. That's what we're given. So that means Q, the population proportion of failure, the people that fail at using Chrome, that's always 1 minus P. Make sure you have all this written down in your notes. $65. So 1 minus, oops, minus 0.654, 0.346. So 34.6% of people don't use Chrome. They fail at using Chrome. Okay, we find our standard deviation. I'm going to start writing. So the standard deviation, according to the central limit theorem, I don't need it. Let's make it nice and thin. Where's that coming out? Oh, right there. Standard deviation will be square root of PQ over N. A lot of mistakes happen here. Make sure you know how to type this into your own calculator. N here is the sample size, 221. All right, so we type that in our calculator. In my calculator, I can just type it. Square root some of you, your calculator, you may have to put that top in parentheses. I just need to make sure that everything I'm typing is underneath the radical. Like that. That's the answer I should get it. Try it on your own. If you get a different answer, you're typing it in wrong. Make sure you know how to use your calculator. 0.032. We'll go to 3 places. Okay, now, like on that weekly assessment that's coming up, I asked for the model. Let's talk about the model here. So the model, the central limit theorem says we're supposed to check our conditions. So I'll write that down. But I'm not going to write down checking them. I'll just say we've checked the conditions. The conditions are, did you do a good sample? Well, I hope so. Like, I didn't do the sample myself, right? Like, I made up these numbers, but whoever did the sample of these 221 people, if they did their sample at Microsoft headquarters, then they're probably not taking a good sample, because at Microsoft headquarters, I'm sure you have to use Microsoft Edge, right? Because they make it. That would be a crappy sample. So we just got to assume whoever did the sample did a good sample. We're supposed to check that P times N is bigger than 10, P times Q is bigger than 10. We're supposed to check all that. We're supposed to check the sample's independent. I'm not going to bother with any of that. Let's just pretend we checked all the conditions and we meet them all. We do. Then central limit theorem says that all possible sample success rates follow a normal distribution. When I say, tell me the model, that's the sentence you would write. The p-hats follow a normal distribution with mean, mu, equals the population success rate, which was 0.654. That's an equals to there. I'm going to upload this document that kind of look like not equal to. And the standard deviation of 0.032. So that would be, if I ask you for the model, all of that, you have to say all of that. Okay, now we can start thinking about the question. We did a sample. That sample is someplace on this normal distribution we're talking about. Let's draw it out. So these are all possible samples of size 221. Right in the middle, the mean, the average sample success rate would be exactly the same as what the population is. It would have 65.4% of people using Chrome. I did a sample. I want more than 60% to use Chrome. So here's the p-hat I'm interested in. I want this area. So here's my sample. I'm always going to have an X, an N, and a p-hat. They're always going to give me 2 out of the 3 here. Always. So I want a sample success rate of 60%. And my sample size was 221. X is always p-hat times N. Or going down, if they give us these two, p-hat is always X divided by N. So 0.60 times 221 I get this, 132.6. You can't have half a person. X is the actual number of successes in the sample. You can't have 0.6 people. We have to round that. That's going to be really important later when we get into confidence intervals and hypothesis testing. You got to get used to this. We have to round X to the nearest whole number. We're going to call that about 133. And that might bother you and go, wait, we shouldn't be rounding. We actually didn't round. We fixed it. They rounded that number. So whoever gave us that number, that's a rounded number. This is what they actually found. 133 people in the sample said, yeah, I use Chrome. And then they did 133 out of 221, got a number, and then they rounded this when they told it to us. Okay, so now we're in a chapter 5 problem. I've got a normal distribution. I know the mean, I know the standard deviation. I've drawn a picture, draw a picture, find z-score, normal CDF. There's my picture. I find my z-score. Now you can memorize this formula if you want. I don't have this memorized. I'm figuring it out as I write it down. By the way, if you don't know what all the symbols stand for, forget it. You're not getting anywhere with this problem. You got to know what all the letters stand for. Don't memorize the formula. Draw the picture and think, okay, z-score is the one I want minus the one in the middle divided by that standard deviation I just calculated. So 0.60 minus 0.654 divided by that standard deviation I just found. Okay, remember when you're doing z-score, do the top, hit enter, then do the dividing. So there is my z-score, -1 point, I'm going to go to 2 places, -1.69. So that's this guy's z-score right here. So his z right here is -1.69. What's the z way up here? That z equals infinity. So now I'm going to do normal CDF, smallest z-score to the biggest. Now, ideally, we would type in infinity, but I can't type that in the calculator, so I'm going to type in 99. Second distribution, number 2, -1.69 up to 99. Leave these two alone because we're using z-scores here. 95.4%. So then word problems have word answers. The probability that more than 60% of the sample, remember, we're not making predictions about the entire population. We're making predictions about samples. Use Chrome is 95.4%. Or another way to say that is if you were to go out and do billions and trillions of different samples, if you were to do an infinite number of samples, 95.4% of those samples would have a sample success rate more than 60%. So here, I'll type that just for completeness. There's another way to say it. Okay, let's look at another problem here. So pause and read the question. So first thing we got to decide, is this a mean problem or a proportion problem? They say the word mean right there. It doesn't look like the word mean. Sure it does. Mean and average mean the same thing. They give me a standard deviation. There are no percentages anywhere. This is a mean problem. So completely different formulas, completely different variables. So here, I'm going to add in a part here. Let's define the variable and give the model. So what we're talking about here are population means. So the first thing we have to do, a required step here, is define what is it we're talking about. What is it we're even putting on a normal distribution? It's the population mean. What's my population? The length of this group. We don't have success or failure here. Mean problems don't have success and failure. They don't have P's or Q's or P hats or Q hats. They have mu's and X bars. So let mu, that's my first step, define my variable. It's a required step. A whole lot of people lose a point here. Let mu be the mean length of this part. We're told that the population mean is 10.2 inches. And we're told that sigma, the population standard deviation, is 0.2 inches. Okay, now we're supposed to check all of our conditions. So did we take a good sample? That's what we're going to find out at the end. In the real world, you go out and you do a sample and you're not sure if your sample is a good sample sometimes. You wait until you see your results and you go, oh, wow, I think something was wrong with my sample. That's what's going to happen here. I think I made up this problem 20 minutes ago or so, but I'm pretty sure we're going to find out, oh, something's wrong with this sample. But we won't know that until we do the math. No, like if you're sure something's wrong with your sample, obviously you can't do the math. But let's pretend for a minute we got a good sample. We're supposed to check, is our sample size big enough? How big is big enough? It depends. If you're told the population is a normal distribution, you can use any sample size you want. If the population is nearly normal, then you can use a small sample size. You can get by with a sample size of 4 or 10. Otherwise, you need your sample to be, like the guideline I was always told was at least 50. My sample size is 160. That's big enough. So check the conditions. Then the central limit theorem says that all possible sample means, the X bars, that's the sample mean, follow a normal distribution with the mean equals the population mean, 10.2 inches, and the standard deviation equals the population standard deviation divided by square root of n. What's n? What's my sample size? 160. So that'd be 0.2 divided by square root of 160. So 0.2 divided by square root of 160. 0.016, we'll call it. I'll go to 3 places. So all of this here, when I ask for the model, you'd have to write all of that. Define your variable. That's what this is. That's naming the model, giving the mean and the standard deviation. Notice that it's not the population standard deviation. I'm not talking about individual parts here. I'm talking about samples of parts. Okay, so now let's find the probability that they got the sample they got. So we draw our picture, same 3 steps always. Draw the picture, find the z-scores, normal CDF. So right here in the middle, remember what I'm graphing here, not individuals. I'm graphing samples. The mean of all possible samples, the average of all the averages is 10.2. The standard deviation is this one that I just calculated. I want to be at 10.4. Now, you always got to shade something. So they didn't say above or below that. We don't have the ability to find the probability of hitting one number exactly. We always have to go above or below that. And if we're not told which way to go, we always shade a tail. Need more space there. So I'm going to shade in this tail here. Shade above that. So what I'm really going to find is not the probability that they got 10.4 on average. It's that they got 10.4 or more. Hey, I find my z-score. Now, again, you can memorize the formula here. Z-score here is x bar minus mu over the standard deviation of all possible x bars. Like, I don't have that memorized. I just figured it out on the fly. Don't think like that. Think, okay, the one I want, the one they asked me about in the problem, minus the one in the middle of my picture. That's why you want to draw a picture, divided by that standard deviation that I just calculated. So 10.4 minus 10.2 divided by 0.016. A lot of mistakes happen here. People use the wrong standard deviation. So we got 2 different standard deviations floating around in the problem. This is for individual parts. This is for samples of 160 parts. All right, let's throw that in our calculator. I get a giant z-score. Remember, a regular old z-score is like between -3 and 3. Those are big. I get a gigantic z-score. That's the point of this problem. I get a z-score of 12.5. And immediately I should go back and check on my work and make sure I didn't goof. But then if I read the question and I go, oh, okay, like that's the point of the question. Is that something really weird is happening here? See, if this were one individual part, think about our setup here again. The average, this company makes this part, it's 10.2 inches long, but that's just the average. These things vary. The standard deviation is 0.2. So if one part comes off the line, they grab one of it, and it just happens to be 10.4, that's only one standard deviation above average. 16% of the population, if the thing is normal, 16% would be there or above. Like, that's not unheard of. It's no big deal. These things vary. They got a pretty big variance there, pretty big standard deviation. So like 16% of the individuals would be that big or even bigger. We know that from empirical rule. But that's not what we're talking about here. We're not talking about one of them is that big. We grabbed 160 of them. Those things should be all over the place. Some of them should be up here, some of them should be down here. If it's a good sample, the individual should be all over the place. So if we average them together, they shouldn't all be big. We shouldn't get an average that's this big. Getting an average that is that big is 12.5 standard deviations above what we would expect. That's a gigantic z-score. So back to our problem. That was his z-score there. I shaded all the way up. So up here is z equals infinity. So normal CDF. Smallest z-score I shaded up to biggest. Again, we'll put that in the calculator as 99. So 12.5 to 99. You will never get a probability bigger than 1. A lot of mistakes happen here. Look at that answer. That is not 38%. That is not 3%. That's 3.8 times 10 to the negative 36th power. Look right there. Anytime this comes out bigger than 1, you got to be careful. Look at that. So that was 3.85 times 10 to the negative 36. That's an incredibly tiny number. Almost impossible. So that's the probability of getting a sample average that's 10.4 or bigger. I'll type that up. Of sampling, what was my sample size? 160, I think. Yeah. Of 10.4 inches or more is 3.85 times 10 times 10 to the negative 36. So now part B here, I guess this is really now part C. What's that mean? Let's think about this. We own this company. We know that our parts vary a little bit. We know our machines aren't perfect. We're trying to hit 10.2, but there's a little wiggle room there. We grab 160 off the line, and they're not all big, but their average is much bigger than it should be. The probability that this was just a random sample, like, it's possible that there's nothing wrong with the machines. We just happened by chance to just grab a whole bunch of big ones off the machine here, off the conveyor belt. It's possible, but it's very, very unlikely. The more likely explanation is something's wrong with our machine. It's making these bigger than they should be. So I would say yes. probability. Basically, what we found up here was the probability that that was a good sample. If that was a good sample, that's the probability that we just pick those at random. So there, like I just said, there are two possibilities here. I guess three possibilities. One is we goofed somewhere, but we double checked the math. One possibility is we did a good sample. There was nothing wrong with our sampling technique. It wasn't biased. The machine's working fine. We just by chance happened to grab a whole bunch of extra long parts. Or there was something wrong with the sample. What do we mean? Why would there be something wrong with the sample? Where are we getting the sample from? The machine is spitting them out. Like I just grabbed them at random. The machine's supposed to be spitting them all out the same size. There's probably something wrong with the machine. So I'll kind of type that up. If that was a good sample, there's a very small probability. I don't know why I can never type probability of getting a sample mean that large. It was more likely a bad sample, meaning there's probably something wrong with the machine. Like this is real world stuff. This companies really do this. And I'm not like, it's not like we're covering up the details here. It's not like in the real world, they actually use a more complicated formula and we're just not telling you about it yet. No, this is real. Like the real companies do this. You pull one off the assembly line and it's a little tiny bit long and there was some variance in there. Getting one, not that big a deal. You pull 160 off and your average is really big and there's probably something wrong with your machine.